Mikael Agn. So let's start about talking about the difference between mutual information and sum-of-square difference as similarity metrics. So sum-of-square difference is for uni-modal images, and it has an associated probabilistic model, which means that you can explore the probability distribution, get uncertainty, and so on. Then it can also be used with a fast and dedicated optimization algorithm called the daemons. And then mutual information is for multi-modal images. Currently doesn't have an associated probabilistic model, and methods using it use general purpose optimization algorithms, which can be quite slow. So the contributions of our paper is to recast mutual information computations with partial volume interpolation as a generative model, and then using the structure of this model to derive an expectation-maximization algorithm, which is similar to daemons, and then a Gibbs sampler for uncertainty estimations. Yeah, so we want to register image U with the image V. Here we have U as a T1 weighted image and V as a T2 weighted image, and we have we have different contrast properties. As in mutual information, we discretize the intensities in the images. Here it's we have discretized them into 4 levels. Obviously, we use more in the actual when we actually use the model, but this is just to illustrate the model, and I have it in 1D here in order to illustrate the model. So the generative model. So we want to create a model to generate U from V, and we use latent variables n to do this. Once we have created the model, we register U with V by fitting the model parameters to the data. And here I'm showing the posterior of the model parameters. We have a deformation field D and an intensity parameter or intensity parameters in theta. So let's start with the deformation field. We have a deformation prior just to encourage smoothness. And here we have generated a deformation field from this prior. And then let's focus just on one voxel with a deformation vector here. Now we want to generate latent variables, and we do this by centering a B-spline at each deformation point. We have each deform point, I mean. So we have the deform point pointing somewhere in the space of V, but not at a specific voxel location in V. And then you can see the B-spline centered at that location. And the latent variables that we have are basically, okay, so now this doesn't work so well, but the latent variables are a connection between one of the nodes in V to a location or the voxel in U. And this looks okay. And here we have all the latent variables connected. So it's one connection. Each voxel in U have a connection to some voxel in V. And once we have these connections, what we need to do is to have a model to generate intensities in U through some intensities in V. And here I'm showing the intensity parameters that we have in theta. So they work like that, but for each intensity or each class in V, we have a probability distribution which gives the probability of different intensities in U. So now, because of we are trying to do mutual information, they are binned probability distributions, but obviously we could use any kind of distributions. If we would like to use some square differences instead, the distributions could be just conditional or continuous Gaussians centered at the same intensity as the intensity in V. So now we focus on one voxel in U, which is connected through the latent variable to a location or a node in V. So here I've indicated the probability distribution of the class in V. And as you can see, the highest probability is for the intensity furthest away from us in U, which is the darkest intensity. So we fill that in. And then we can do that for all locations in U. And we have generated U from V. And obviously we also have a prior on the intensity parameters theta as well. So just to summarize the generative model, we have priors on the parameters, on the deformation field and the intensity parameters. And then we have a joint probability over U and N given the parameters. We have defined the probability of the latent variables N given the deformation field, and we have defined the probability of U given N and theta. So this together, all of these ones, form our model. Then we can marginalize or sum out the latent variables, and we get a probability of U given the model parameters. And to register U with V, as I said before, we just maximize the posterior of the model parameters, which is shown here below. Yeah, so how do we do this? Because of the structure of our model, we can use an EM algorithm, and as an EM algorithm, so an EM algorithm have weights that are updated on the current model or the current parameter estimates, and then updates for each parameter, which you iteratively circle through. And the weights in this case would be soft node assignments. And then here I have the update for theta. So theta, I show here an example. So I show an example of theta with 32 bins. So you have 32 bins of in U and 32 bins in V, and yeah, this looks like a joint histogram in mutual information. The only difference is that it's normalized. Each column is normalized to form a probability distribution. And as you can see, so theta would basically each of these bins in theta is weighted sum of the intensity combinations. So it's very similar to mutual information with partial volume interpolation. So then we go to the update for the deformation field. So we don't have that in closed form. So we are using an approximation. We approximate the B-splines with Gaussians to get it in closed form. And here I'm showing a cubic B-splines together with a Gaussian distribution with the same height. And as you can see, it's a fairly good approximation. So here we have the updates for D. You can see it as having it 2 steps. You have some dream deformations in delta that are very noisy, not regularized. So that would be in the first step, and then in the second step you smooth these dream deformations with a smoother matrix S, and we do this with the FFT to make it quick. So this is the way how it's similar to demons, that you just get some noisy dream deformations, you smooth them, and then you repeat. So with the Gibbs sampler, it's very similar. It's the modes of each of these distributions of the conditional probabilities of the different variables and parameters we have. The modes will be from be the same as the weights and the updates in the EM algorithm. And the important thing here with the deformation fields is that so they are normally distributed, and we saw that also in frequency domain. We do most of the computations in frequency domain, and we do sampling in frequency domain to make it fast. So how is this equivalent to mutual information then? So we do a small experiment here, just a translation experiment, the same subject, a slice of the same subject, and we move just one of the images a few voxels in each direction. And as you can see, our model and mutual information is the same for 0th order B-splines, and it would also be for 1st order B-splines at each voxel location. It would be the same. And 3rd order B-splines, it will look very similar. Okay, so the experiments that we have done, in the experiments we've done, we've used 6 subjects that were registered to 10 subjects. So we have 60 registration pairs, obviously in 3D. We're varying the flexibility with the highest model flexibility close to what we would use in demons. We use 4 resolution levels with 100 iteration in each. And here you can see an example with the T2 weighted V and T1 weighted U. We have it deformed here with our EM algorithm. And then we also have segmentations, which we will use to compute die scores as an accuracy measurement. And we compare it to Elastix, which is a free-form deformation method using mutual information, and because we cannot compare Elastix and our model exactly, we vary the model flexibility of each and the number of iterations. And if you look at the first plot first, is the computation time. We can see that for the lowest degrees of freedom, which quite often would be used with Elastix, our model is comparable in computation time as the Elastix, but when you go up in degrees of freedom to something closer to what would be used in daemons, Elastix become very slow. And then we can see the dice scores for it's an average of the 10 largest structures in the brain. Our dice scores are first, and then we show for Elastix. And ours, the accuracy of our method is slightly better. So now let's check at the sampler. And we do draw 20,000 samples from the joint distribution of all variables. And first I show the standard deviation over all these samples. Then U, the T1 weighted image, and then the T2 weighted image deformed by 7 different samples of the deformation field. So what you can see here, for example, in this region, the EM estimated deformation field, the estimated mode of the deformation field, is quite well registered. And we can see that the samples are not changing a lot in this location. But for example, in this location, it's not very well registered, the two images. And we see that we have quite a lot of variations between the samples. Yeah, and then we also, here I just show the estimated posterior over all the samples after the burning phase, obviously, of the gamma parameter, which measures the model flexibility, or the flexibility of the deformation field. Yeah, I'm not sure how much time I have.
Yeah, I think we should be coming to the conclusion.
Just wanted to say that we have also compared to daemons, and it can serve as an alternative to daemons in sum square difference. So just to summarize, we have made a fast, dedicated optimizer for mutual information that also can serve as daemons, as an alternative to daemons in sum square differences in mutual information as well. And then we have a Gibbs sampler where we can do uncertainty estimations for mutual information. And in the future, we would also like to see if we can make it differable.
Okay.
Thanks.
Thank you. We have time for one or maybe two quick questions. Perhaps I can start. So I didn't quite get in the end. So is the connection to mutual information just something you get from observation, or is there actually a link to information theory and so on mathematically as well?
So the connection would be that well, maybe it's easier to show it here. So the updated equation we get for theta would be similar to how you compute mutual information with partial volume interpolation.
Okay, thank you very much. Do we have any other questions for the speaker? Okay, so in that case, let's thank the speaker again. And let's move on to our last